Alright, so we are going to talk hydronic systems. So we'll just start off on the PowerPoints and then we'll expand from there. Normally, as I was talking a little bit about earlier, I would start with pumping away on this stuff and boiler piping in general. But we're just going to see where these PowerPoints lead us and go from there. So, when we've completed this lesson, we should be able to do the following. Describe basic concepts related to water as a substance and its movement. Describe the basic properties of water and water pressure. Explain how pressure drop, head pressure, and static pressure are related to hydronics. Describe various commercial hot water heating system components and subsystems. Identify various types of hot water boilers and their common controls. Describe the construction of common centrifugal pumps. Give me just a second. Turn that light off a little bit and turn this light on. There we go. That's a little better. Alright, so get ready to play Jeopardy. Read the answer, determine the question that goes with it as quickly as possible. Alright, what are they going over here? Corrosion occurs within boilers and other hydronic system components because of this element that enters along with fresh water. So this is the nice thing about boiler systems, right? Boiler and chill water systems. They're closed loops, okay? So for you guys who don't do that much boiler work, I imagine at some point you've noticed that on boiler systems and chill water systems, a lot of the times it's not like plumbing where you're always using copper or PEX or something that's good for domestic water. A lot of the times we're using steel. Well, how can you use steel for a boiler system, right? It'll rust. Well, the idea is that once you bleed all the air out, right, you get all the oxygen out, there's no oxygen, free oxygen in there to corrode the system. So oxygen, right, what is oxygen? Oxygen is what normally causes rust, right? I'm drawing a blank now. Iron oxide, right? Iron oxide. Or whatever oxide. When you're brazing copper, you create a oxide in the copper, basically, right? That's why we purge it with nitrogen, so there's no oxygen in there while we're brazing, so that we won't form oxides on the inside of the pipe. So oxygen is kind of the catalyst for all these different types of corrosion. But even though there's, hydrogen dioxide, there's water inside the boiler system. Once you've bled all the extra air out, there's really no free oxygen in there to cause corrosion. So that's why you can run these things in steel. Alright, steel, copper works well on boiler systems because, again, the copper is not going to get very thin as quickly as it would with freshwater systems because there's less oxygen and minerals in there to cause corrosion. But this assumes that when you start that boiler system or you start that chiller system, you purge all the air out and it's never opened, okay? Which never happens. But this is always my chief complaint with hydronic systems. You want to be very careful, and you should try and do the best job you can when you're doing a boiler or chill water system, because the more leaks there are, the more problems you have with the system, the more it corrodes, because every time you have to repair it, you got to open the system up. You got to, on chill water especially, you got to cut the insulation off. If you don't put the insulation back on good with a good vapor barrier, then it's going to rust from the outside in because of condensation forming on the pipe. Every time you open the system, you introduce more oxygen back into the piping system. Once you introduce oxygen into the piping system, that's going to corrode it just a little bit more until all that oxygen gets purged. And the more repairs you have to do, the more repairs that will need to be done. Because every time you open it up, you're just exposing it a little bit more to problems. So you basically got two options. You make it out of a really good piping system that will not be as corroded as easy, so use less iron components, use more brass, copper, stainless steel, things like that, or use all steel components, but try and do a very good job from the beginning so that it doesn't need to be opened up very often. Put a lot of valves and things that need to be serviced so you don't have to drain a lot of the system to make certain repairs. All these things are extremely important when it comes to hydronic systems, so it's something to keep in mind as you're piping it. How can I make sure that this is as serviceable as possible? And how can I make sure that even when repairs need to be made, as little oxygen as possible is going to be reintroduced to this system. On chill water especially, anytime you got to make a repair and you got to put insulation back, make sure you do the insulation very well with a very good vapor barrier, or you're just going to cause more problems down the road. I have a very love-hate relationship with hydronic systems because of that. Because they're real nice when they're done, when they're piped well, and when they're not piped well, they're just nightmares, and that just turn into bigger nightmares, that just turn into bigger nightmares. You know, and people like to start piecemealing repairs, and you start, again, you make a repair, you're causing more problems, you make another repair, that causes more problems, so on and so forth. Alright. What's next? In a given length of pipe, the pressure drop of flowing water quadruples when this factor is doubled. Ooh, I don't know this one off the top of my head. The pressure drop of the flowing water quadruples when this factor is doubled. The velocity? The flow rate. Same thing, basically. So the faster the water is flowing through, the more the pressure is going to drop. So generally when we're sizing boiler piping, we're keeping the velocity. It's everything. Pretty much everything you have to take velocity into account, how fast the water is moving. You have to take into account how fast the water is moving along in the piping, because based on the size of the piping, I like to bring it up when I'm talking about ductwork, right? Because you have the square free area of the duct, right? And then you have how fast the air is moving in the duct in feet per minute, and that gives you cubic feet per minute, right? You got 2 dimensions from the duct and 1 dimension on how fast it's moving. It's the same with water. We're still moving in feet per minute, right? So the water is, you've got the area of the pipe and then how fast the water is moving through the pipe, and that's going to give you your GPM, your gallons per minute. And the faster that GPM is, the louder the water is going to be in the piping system, and the more that the friction in the piping is going to act on the water, right? So it's just like driving a car fast down a road. If you're driving your car at 30 miles an hour and you let go of the gas, it'll slow down a little bit less than when you're moving at 100 miles an hour and you let off the gas. It's going to, it's going to drop to that speed. It's going to drop to a lower speed faster because the air moving across of it, not only the drag, but just the friction of the air moving across the car. There's a lot of friction involved there in it. The only air is from, the only friction, is from the air, right? And in piping and duct, we've got friction from the air or the water moving against the actual surface of the pipe, which can be pretty rough, especially when you're talking steel. And elbows and stuff, cause a lot of pressure drop as well. So pressure drop is always important, and you're always trying to find a happy medium on velocity to where you're not moving too fast, but you're not moving so slow that, you're just making your pipe so big that it doesn't make any sense. All right, so these are all things to think about. All right, Schedule 40 PVC pipe is used to vent this type of equipment. What is Schedule 40 PVC pipe used to vent? Are they talking about just high efficiency equipment? Condensing, yeah. Alright, so they're just talking condensing equipment. I think of vent, and sometimes I don't always think of flue vents, right? So they're just talking about high efficiency boilers and stuff. High efficiency boilers or furnaces, obviously, if you guys don't know, you vent with PVC because the flue temperatures are so low, because we're extracting more of the heat out. So you've got 80% equipment, which is always metal pipe, right? And then you got the high 80% equipment, like 80% and less you can do in galvanized. You get into 85 to 90%, and now it's hot enough that you can't use PVC, but it's corrosive enough because of the condensate that you have to use stainless. So most of your stainless steel boilers are in the 85 to 90% range on efficiency, and then once you get above like 92%, the flue gas is actually cool enough that you can vent with plastic. PVC pipe. Here's an interesting note. The funny thing about PVC pipe being used for venting is that it is approved by the equipment manufacturers, but it is not approved by the piping manufacturer. So I don't know if they're still doing it, but there was a really hard push for a while there for that polypropylene venting piping, because the PVC pipe manufacturers were saying, we don't care what you do, but we're not warranting our pipe. So in other words, the equipment manufacturer has to take the responsibility for the listing when you're using the PVC pipe for it. They don't want to be liable for any issues caused from PVC pipe being used for venting a gas appliance. So that's where a lot of that plastic, like polypropylene gasketed piping comes from, is the fact that they'll actually say their piping is good to be used as a flue vent, whereas the PVC pipe manufacturers will not. If you read their manuals, it is not to be used for that. So it's just something to keep in mind. It's not really the thing to be wary of when it comes to using PVC pipe for venting, and something you want to think hard about if that's what you like to do all the time, which is, most guys, especially when it comes to boilers. You want to try and keep that flue temperature as low as possible, or the water temperature in that case, because the higher the water temperature, the higher the flue temperatures are going to be. So if you're running your boiler at 180 degrees, your pipe, the flue temperatures are always going to be right on the verge, right? They're always going to be right there on the edge of being too hot for the PVC. So all you need is some kind of issue where the water overheats a little bit, and you're going to end up with an issue where your flue temperatures go up, and now the PVC is all but melting, okay? Your glue joints start to leak because the glue starts to break down and all that nice neat stuff. So usually what I say you should really think about is, if you're running a commercial boiler system where you're going to have flue temperatures, or not flue temperatures, but water temperatures that exceed 100 or meet or get close to 180 degrees, then I would probably recommend polypropylene plastic or stainless steel vent. If you're running less than that, if you're running 140, 160 degree boiler systems, or even better, 120 degree like radiant heat systems or something, then PVC is fine all day long. That's just my 2 cents. I don't think you'll find that in a manual anywhere or anything like that. That's just based on when I looked at where your temperatures were going to run and what your flue gas temperatures would be at those temperatures, and so on and so forth. That's kind of the rule I came up with. So usually I won't say spend the extra money on that expensive venting unless you're running high temps. 12 psi is the common factory setting for this hydronic system device. And we're going to talk about this in detail too. Alright, what is the pressure reducing valve? Give me just a second, guys. Sorry. Everybody and their mom's texting me right now. Alright, so anyway, 12 psi is a common factory setting because it's good for residential, and you know what, I don't want to go into this in depth yet. Let's see what else stuff is in here, but we'll talk about why psi is the common factory setting on a PRV. We were going to get into that deeply. Alright, a given weight of water can carry more heat than an equal weight of air because this because this water characteristic is also higher. It should be like the density or the specific heat. Specific heat is rated. So the specific heat of something is, or the specific gravity is just, it's based on its mass. Okay, so water has more mass than air. And, you know, I'm not a physicist, so maybe I'm saying this wrong, but this is how I think about it. But because that mass is greater, it can hold more heat per unit, right? The water is going to be able to carry more BTUs per cubic foot than a cubic foot of air is going to be able to. So that's how I think about that. Alright, our acids are also found in this byproduct of condensing boilers and furnaces, and that should be the condensate. We already talked about the temperature of this stuff a little, or yeah, the flue. The condensate gets created in the flue, and the condensate is corrosive. Alright, the condensate is not that corrosive. I think it's overplayed a little bit how corrosive flue condensate is, but it is corrosive, which is why you see everybody doing neutralizers now. In commercial, it's required by code at this point. It's not really required by residential, but it is to the point where neutralizers are required in commercial. And I think that's also a little overstated, because really if you're using plastic waste piping, there's really no reason for you to worry about the acidity of that condensate. As far as I know, I've never heard a good argument on why you need a neutralizer if that condensate's going to be entering a plastic piping system. But if it is entering a metal piping system like cast iron, then or copper even, then that corrosive nature of the condensate can be an issue. And the city's mainly trying to protect themselves on their main piping. They don't give a shit if you eat up all the piping in your building. They don't want you to eat up their older mains and stuff like that. So that's why we do neutralizers on flue condensate. Alright, PEX tubing is now commonly used for circulation of hot water in this type of radiant heating system. And that would be underfloor heating. Well, usually, colloquially in our trade, right, we just call that radiant heat. Alright, so the fact that they call it radiant heating, most of us just understand that that means underfloor or in-floor heating. And then other forms of radiant heat are specific, like baseboard systems, convectors, radiators, things of that nature. Radiators is a radiant heating system, but we don't think of radiator system as a radiant heat system most of the time. Maybe depending on where you're at, you'll call those radiant heaters, but usually if someone says radiant heat, that means it's underfloor. Try and... how do I open the chat when I've got this open? Just in case. I guess if you guys got questions as I'm going through, just text me, alright? If you end up having any questions, just text me, so I don't have to figure out how to open the chat. Alright, dang it. Alright, water is a chemical compound consisting of oxygen and hydrogen elements. It can exist in 3 states: solid, liquid, and vapor. And that's most things. Most things can exist in those 3 states. As a matter of fact, is there anything that doesn't exist in those 3 states? I guess maybe, but pretty much anything can exist in those 3 states. It just depends what temperature they become in those states, as we should understand as HVAC guys, right? But as its temperature increases, its weight decreases. Changes in water weight can cause natural or thermal circulation in a closed system. Anything, right? Is one of my pet peeves, right? Heat doesn't rise, alright? Heat does not rise. If anybody tells you heat rises, they're full of shit. Heat goes from greater concentration to lesser concentration. That's what heat does all the time, right? But a warm fluid will tend to rise. So warm air, which is a fluid, tends to rise. Cooler air, which is a fluid, tends to fall. Same thing. Warm water tends to rise. Cool water tends to fall, whether you're talking about in a water heater or in a piping system. So, older steam systems and didn't have circulator pumps, right? Newer steam. I think they did it with hydronics too, but I can't remember of a specific example. Steam systems don't have pumps really anyway, except for on the condensate side, but you would have like one pipe steam systems and things like that, and basically the steam rises and then the condensate drains by gravity back to the rest of the system. You can design a hydronic system probably so that it doesn't even need a pump. Even when a condensate or a hydronic pump fails on a boiler system, especially in like a house or something, when the boiler's on the first floor, a lot of times they'll still get heat from it because the warm water will tend to rise, the cooler water will tend to fall, and they'll still get some amount of heat performance out of that. So until they have a pretty cold day, they won't realize that their circulator pump has failed. That's not uncommon. The changes in the water weight, the changes in the weight of the fluid is what causes circulation in a system, or causes that air to rise. Same thing with the flue. Our 80% and lower equipment, the flue gets vented out of the chimney because the warm air tends to rise. The warm flue gas tends to rise up through the flue and up through the chimney, and that causes a stack effect, right? So the warm fluids rise, but heat does not rise. All right, adding makeup water to a system introduces excess oxygen and other minerals, leading to corrosion and scaling. Again, minimizing how much water you introduce into a closed loop will exponentially increase the life of that system. So you want to have good, tight systems with very little leaks. One thing I recommend on boiler systems, especially if it's your own boiler system, say in your house or something, is to turn off your makeup water valve, right? Really, you should never have to make up water into the system. There's always going to be micro leaks and places where the water escapes, but it should be extremely slow if everything's nice and tight. So the best thing to do is to turn off the makeup water and wait till you have a problem, and you can see when you're losing water. But really, there's no reason to have constant makeup on a system if it's a nice tight system. All right, you should only have to fill it once, theoretically. It's not how it works in the real world, but theoretically you should only have to fill that thing once anyway. All right, water pressure. I want you guys to pay special attention to this, and this bottom part down here is how I remember it. So the formula for computing pressure in pounds per square foot, all right, the P is the pressure per square foot, D is the depth of water in feet. So this is the weight of the water. All right, the weight of the water is 124.8 pounds per square foot. Wait, what are they doing here? P, 62.4 times D, the depth of the water. Okay, yeah. So 62.4 pounds per square foot at the bottom if the water is 1 cubic foot. If the water is 2 cubic foot, then it's 124.8 pounds per square foot. So this is just the weight of the water. All right, the weight of the water itself, so that you understand how much that piping is going to weigh, or how much that cylinder is going to weigh when it's filled with water. I generally don't calculate this like this, but I usually try and convert the amount of water in gallons, and then it's like what I don't know, I'd have to look it up. I got it somewhere. It's like 7.5 pounds per gallon, and then 8.33 gallons per cubic foot or something like that. Some crap like that. I'll see if I can pull it up before we're done, but I usually calculate the volume and then figure out how many gallons and multiply it by the weight of water per gallon. But if you remember 62.4 pounds per square foot, you can do it like that. This is basically pounds per cubic foot too, I think. Yeah, that should basically be pounds per cubic foot. But that's assuming you have a 1 square foot at the bottom. So it's not, to me, it's not the best way to think about it. But this at the bottom is important. Formula for computing pressure in pounds per square inch. So no matter how big this is, right, you can have this cubic foot amount of water, which is 62 pounds of water, right? But since it's only 1 foot high, it's going to be the same PSI at the bottom if it was, no matter how big this water is, it all depends on how tall it is, right? Because it's going to exert the pressure down. And since we're talking about pounds per square inch, that pounds per square inch doesn't change no matter how big the volume is. So if that doesn't make sense, let's talk about it more, and hopefully it'll start to click. But this 0.433 is really important, all right? So P is the pressure per square inch. I wish they wouldn't use the same variable there, but whatever. And then D is the depth of water in feet. So for every foot of head, and I want you to remember this because we're going to use foot of head in a couple different ways, but it's really all the same thing. Every foot of head is 0.433 psi. 10 foot of head is 4.3 psi. A lot of people round it up to 5, okay? 10 foot ahead is about 5 psi. Is it really 5? No, it's 4.33. But 10 foot ahead is about 5 psi. Try to remember that because it's important to remember. If you can remember 4.33, great. If you can't, just remember that 10 foot ahead is about 5 psi and you'll get there. All right? So this water right here, right, that weighs 62.4 pounds per square foot has 0.433 psi at the bottom of it. So it's a half a pound of pressure exerted at the bottom per square inch. All right, so no matter if you stuck a pressure gauge at the bottom of this column of water, it would be 0.433 psi. All right, this 2-foot column of water is double that, right? It's 0.866 psi. So even though this thing weighs 124 pounds per square foot, it only exerts 0.866 psi of pressure because it's pounds per square inch. All right, so psi is, it doesn't matter how big this is. This water, this 2-foot tall water, this could be a pool. Okay, you got a pool that's 2 foot deep. That whole pool is at the bottom of that pool. The pressure is 0.866 psi. All right, so don't worry about the weight of the water when we're talking about feet of head and things like that. It doesn't matter how much the water weighs. It matters how tall the column of water is. And for every 10 foot of that column of water, it'll be about 5 psi. And that's how we use manometers. The reason we use feet of head to measure things is because for small pressures, we measure in inches of water column, right? So 28 inches of water column, all right, is 1 psi. So if you do the math, you'll find, 12, 28 times or 2.8 times 0.433 or whatever will equal 1 psi, right? 28 inches, about 28 inches of water column is 1 psi. So you can make a manometer that's 28 inches tall, a U-tube manometer, and you can measure up to 1 psi in it. Sorry guys, I need just 1 second. And then we'll go over this and then we'll talk more about psi and feet ahead. Stuck watching my kids too. Alright, so pressure drop equals 5 psi. So if you're measuring 25 psi here and 20 psi here, you're moving 5 GPM. They're talking about your pressure drop, and that's when we'll get into feet ahead, but we'll talk about this stuff a little bit more. Let's just read this and I'll expand on it more later. Alright, the movement of water through piping is resisted from the friction of the pipe walls and other obstructions, so elbows, valves, things like that. Pressure drop is the difference in pressure between 2 points in a hydronic system resulting from this resistance. So the final GPM divided by the initial GPM squared times the initial pressure drop equals your final pressure drop. So that's one way to determine your pressure drop. I don't know if this formula is necessarily that important, but it's nice to have around. This is one way that you can determine what your actual pressure drop is. You can measure the pressure drop, but most of the time we're going to talk about pressure drop in feet of head, because feet of head's another way to measure pressure, right? So when we're talking about sizing pumps and things like that, we're going to say how many feet of head. And that gets into the feet of head a pump can handle is basically just how much pressure it can produce. So usually we don't think of pressure drop like this, at least in residential light commercial situations. So again, head pressure, talking column of water, feet of head. Gauge reading of 1 psi is 2.31 feet of water, or like I said, I think it's 28.8 or something inches of water column. Where's my phone? I can do the math, right? 2.31 times 12. 27. Oh yeah, 28 inches, 27.7 inches, whatever. 28 inches of water column is about 1 psi. All right. So the formula for converting head pressure of water in feet to pressure in psi is the foot of head times 0.43. Right? We already learned that. The formula for converting pressure in psi to head pressure is 2.31 times your psi. Either way, you'll get the you can convert one to the other because they're the exact same thing. So it really confused me for a long time, why we looked at feet of head on boilers. But if you learn about boilers, you'll figure out that the height in the feet of head that you lose is just another way of thinking about the pressure in the system. So think of those things as interchangeable. We just tend to use head pressure because it's an easier way to think about the things once you get used to how you need to do it. So if you got a column of water, this is showing a 30-foot column of water, right? So a 30-foot column of water would be 12.9 psi at the bottom, right? It'd be 8.6 psi 10 feet up, 4.3 psi 20 feet up, and 0 psi at the top. So let's think about this for a minute. Why do you guys think that our boiler pressure reducing valves tend to come set at 12 psi? Well, should be kind of obvious, right? Here's the thing. We only need to circulate water in the system, right? So we need to make sure we have some amount of pressure throughout a boiler system. We don't need a lot. We just need enough to make sure that it's full of water and there's no air in it. So we have to have enough pressure at the bottom of the system, right? So that at the top, we've got at least some pressure left, 1 or 2 psi. It's going to be pretty rare in most residential and light commercial situations, right, that you're going to be dealing with more than 3 stories above the boiler, right? The boiler's in the basement, has to go up to the first floor, has to go up to the second floor, and then we still got all the way to the top of the second floor to work with, right? So most of that stuff, most boiler systems are set at 12 psi because that ensures that we got water filled up all the way to the top of the system. If our boiler was on the top floor, we would only need 1 or 2 psi, right? Because at the bottom it's going to be 12 psi, but at the boiler itself, the pressure we should be reading is just enough that it's completely filled, right? Maybe 5 psi. You just have to make sure that there's enough pressure in the system that you've got a full column of water to fill the entire system. That's, in most cases, that's the maximum pressure you need in the system. So 12 psi is a good starting point for most residential and light commercial boiler systems. Now, if you've got a boiler system that's in a building that's 10 stories tall, well, then you need, about 40 psi, right? If it's feeding that whole 10-story building from the bottom, you're going to need like 45, 50 psi to be able to make sure you got a solid column of water all the way to the top. Otherwise, your pressure at the top is at 0, and you're going to introduce air into the system, most likely, instead of filling it up to the top, because you're going to have air reliefs and stuff like that at the top of the system, right? So those air reliefs will just be at 0 or negative pressure because of, the outside air acting on the system, and you'll introduce air. So you just have to make sure you have enough pressure to fill to the top. So that's where we get that 12 psi from. 12 psi is generally enough that we know we have a solid column of water in your average 3-story-ish size building. If it was only a 1-floor house, you know what I mean? If your boiler was in a house that was only a single floor, you don't really need 12 psi. All you need is like 4 to 8 psi. That's all you need in it, because you don't have to raise the water to a very high height of water column. And that's why your boiler pressure gauges often read in feet of head. Because if you forget these things, it's easy to look at that pressure gauge and go, oh, I've got 10 feet of head in this boiler system, but I need 20 feet of head because it's 20 foot to the top. So I need at least this much pressure in feet of head to make sure I can serve the building. That's where those numbers come from. Alright, boilers heat water by burning some type of fuel. Common fuels include gaseous fuels, natural gas, manufactured gas, LP gas, propane and butane. Oil fuels, lightweight and heavy oils. Solid fuels, coal and wood, or electricity. Some boilers can burn more than one fuel by using a burner conversion or dual fuel burners. Natural gas has become the dominant fuel for new installations. So there's boilers out there that can run on natural gas or oil. Might be able to do natural gas or propane. Might be only natural gas. You don't really see that many coal-fired boilers anymore, but I'm sure there's some out there. But usually it is oil, natural gas, or propane, especially in our area. Copper fin tube boilers. Copper fin tube boilers are nice because they got pretty good heat transfer. They have less heat loss. Can burn natural gas or propane, lightweight and easy to install, and can be installed outdoors using antifreeze solutions. Downside of a copper fin boiler is it's not going to last long as a big heavy cast iron boiler, generally speaking, because the copper is not going to be as robust as, say, a cast iron boiler. But copper fin tube boilers are pretty common nowadays, especially commercial situations. Cast iron boilers often consist of individual cast iron heat exchanger sections joined together. The number of sections determines its total capacity, and I forget what the shortcut is, but each one of these sections are going to be able to handle so many BTUs, and you basically just add sections until you need to. So these are sectional boilers. On the big ones, you can replace just one section. So if it cracks, you can pull these bolts off, pull this thing apart, replace the gasket material that's in between them, usually a type of rope. I forget what it is, but anyway, it's that rope. And then put that back together, bolt it back up, make sure it's torqued to spec, and you can fix just that section. So on big boilers, you'll do things like that. Otherwise, you'll be replacing it. But that's a nice thing. And then the other nice thing about cast iron boilers is, they tend to last a long time. It's pretty hard to get a lot of damage on a cast iron boiler. Usually the worst thing that happens is a section cracks, but it's not uncommon for these things to last 50 plus years. Each section is essentially a separate boiler. So you'll have the burner. During boiler design, sections are added as needed to meet heat load requirements. Cast iron boiler sections, fire brick or other retardant material in the burner section. You got a combustion chamber. The heat goes across these sections of the boiler, and then you basically have little individual vent sections going out. So the heat travels along up in between the sections, and you're exchanging heat between the burner and the boiler. And that's the other thing that's nice about boilers as opposed to furnaces, because these things are filled with water, right? And that water is constantly circulating. These things are a lot less likely to have cracks and stuff like that than furnaces, because furnaces just have the air going across, so it overheats, and they tend to be made pretty thin. It's pretty easy because you got to transfer that heat to the air, so it needs to be kind of thin, right? Furnaces, you basically guaranteed to crack that heat exchanger down the line at a seam or something like that. These boilers tend to be, it's a lot less likely that you're going to end up with a cracked section, as long as everything is operating good. Alright, fire tube boilers. Name of the design implies what passes through the internal tubes, right? The fire passes through the tubes, essentially. So your burn is going in, and then the heat gets burned through the tubes in between all the sections. So you have the fire tubes going through, access plate so you can see inside of it, your combustion chamber, support, access plate to see inside of it. Hot gases are running through the fire tubes, and then goes up through the flue. Another cutaway of a different or water tube boiler. Okay, yeah, this isn't fire tube, this is water tube. Alright, water tube boiler. The water goes through the tube, and the fire goes across of it through the breeching. Water drum, water tubes, access plate so you can see in it, clean it, whatever. Water wall furnace extension. Just another boiler design. Other boilers. Vertical tubeless boiler. So this is a vertical section. I've seen these a few times. And then your electric boilers. So there's just other ways to do it. With the electric, here's your elements. With the vertical tubeless boiler, you'll have a fluid chamber, combustion chamber over here in the middle. Then the water kind of spirals around this section, going up through, and the fire basically passes right up along through it. So that is, you see these are usually really small little boilers, but they work okay. Alright, low water cutoff protects boilers that hold a significant amount of water inside. Water flow during combustion is not a necessity. Alright, so they're talking about steam boilers here, but this could be this is very critical, a low water cutoff on a steam boiler, but it's also required on a hydronic, a water boiler, if you don't have a flow switch. But every boiler needs to have a low water cutoff or a flow switch as a safety, because both those things are extremely important to make sure water is in it or moving in it, because you don't want to create steam when you don't want it, because steam can be extremely dangerous if it's not a steam system. And with the steam boiler, you don't want to have not enough water in the boiler. You can cause damage to the boiler or the piping system. So you always need to have a low water cutoff, or on a system that is filled all with water, you need to have a flow switch. One of the two. Low water cutoffs are often float operated, but they can be electronic as well. You'll have expansion tanks. They're showing a supply main, relief valve, city water supply, fill valve. So if this float drops, so there's not enough water in there, it activates the fill valve and fills it back up until the float is back in the up position. And then this is your return, your condensate pump on your return. Oftentimes it'll go to an actual tank with a pump that pumps it back to the boiler. Copper fin tube units that hold very little water. Ensuring that water flow is consistent is the key to protection. So making sure you have a flow switch. Centrifugal pumps. So this is a base mounted pump right here. So this is your centrifugal pump. You have vanes in here. The water goes in the suction side and then gets pumped up through the discharge. You can have, this is an end suction pump, base mounted end suction pump. You can have inline pumps. You can have a few different designs, but this is your most common commercial setup. So you have the suction port, suction cover. You will usually have a suction diffuser on here. You have to have enough straight pipe that you don't need it. Your impeller shrouds, pump casing, bearings at your pump shaft, packing gland to seal the water from the shaft, wear ring, impeller vanes, discharge port. Those are your most common internal components there. Alright, you have different impeller designs. So this would be an open impeller. This is a semi-open impeller. This is a single suction closed impeller. This is a double suction impeller. And this is a mixed flow impeller. I haven't broken down, come to think of it, I haven't broken down that many impellers to see them. I'm sure these upper two are probably your most common on end suction pumps. This single suction closed impeller is your most common on an inline pump that I see. But, it all depends. All these impeller styles, whether we're talking about for water or we're talking about fans and stuff like that, the impeller and blower wheel designs all depend on how much air you're trying to move. In this case, how much water you're trying to move. Different designs always have different advantages and disadvantages. Alright, special pumps. Horizontal split case design allows for improved service access and assembly for large pumps. So this would be a large split case pump. Alright. So you can see shaft. Looks like a closed suction impeller in the middle there. You can split the case, work on everything, put the case back on top. Hence the name split case. Alright, wrap up trade terms. Boiler horsepower. Boiler horsepower is equal to 9.803 kilowatts. Also, it is the heat necessary to vaporize 34.5 pounds of water per hour at 212 degrees. This is equal to a heat output of about 3,475 BTUs per hour, or 140 square feet of steam radiation. I've never heard that term, so that's a new one for me. Maybe it's a primarily large commercial term, but there you go. That's a boiler horsepower. Fire tube boiler is a boiler with flue gases contained inside the tubes and heated water on the outside. Superheated steam is steam that has been heated above its saturation temperature, so more than 212 degrees Fahrenheit, right? 212 degrees Fahrenheit is going to be the saturation temperature of steam at atmospheric pressure. So if it's above that, then it's superheated steam. Just like we could have a superheated refrigerant, you can have a superheated steam. Water tube boiler is a boiler where the heated water is contained inside the tubes with the flue gases on the outside. Alright. Any questions on that so far? Alright. Let me share this new screen. Alright, when we completed this section, we should be able to do the following. Describe various commercial hot water heating system components and subsystems. Identify various types of valves and other commercial hydronic system components. Identify common commercial piping systems and their characteristics. Alright, we're going to talk about all this stuff. I need 1 second again. Then we'll go through all these components. Alright, so multi-purpose valves. I'm sure, just looking at the picture, they're talking about valves that are usually shut-off valves and balancing valves, or check valves and balancing valves, things of that nature. The most common one is your triple duty valve, which I don't know if we'll see a slide of, but that is your most common valve on a commercial boiler system, is a triple duty valve. Triple duty valve does three things. It is a check valve, a shutoff valve, and a balancing valve. A check valve, a shutoff valve, and a balancing valve. That is a triple duty valve, and they're very nice to use, especially on larger pump systems, because you always need those three things on the discharge side of a pump. So if you can use one component to do all three things, that's very nice. So that's probably kind of what they're getting at here on multi-purpose valves, is a valve that is used, a triple duty valve that is used for those three items. Balancing valves. Alright, balancing valves are really important, okay? One, to balance the water, right? Balancing valves and dampers are all very important components. What's really important about a balancing valve, and what a lot of guys don't understand, a very common mistake I see, not as much on boiler systems, but especially on like water source heat pumps and things like that. Because your connection is 3/4 on the equipment does not mean that you need a 3/4 inch balancing valve. A lot of times these valves are a reduced port. What that means is, in the middle of this valve, it is not as big as the pipe opening. So you can have a 1/2 inch balancing valve that only has a 3/8 port through the middle, because a ball valve or a gate valve doesn't make a very good balancing valve. And like this is a ball style balancing valve. So this is a ball valve in the middle of this balancing valve. This is just basically a quarter turn ball valve turned into a balancing valve. So the only way you're going to get good control out of this ball valve is if it has a smaller port in it in the piping. Otherwise, most of your balancing happens at like the last bit of its travel. So if you need close to the full flow through the piping, right? If you've got a piece of equipment that has a 3/4 connection and needs to flow almost the full 6-ish GPM or whatever that 3/4 inch can handle, then a 3/4 balancing valve is not really big enough. Alright, so you might need a 1-inch balancing valve for connection size of a 3/4 or something like that. Alright, I've seen equipment that have 3/4 inch connections, but they really needed like an inch or an inch and a quarter, inch and a half balancing valve so that you could finely tune the water flow in that range. So it's very important when you're selecting balancing valves to select it based on the GPM that you need and not the pipe size. I want you guys to try and remember that in your career. It's a very, very common mistake I see, and it's extremely annoying when you've got low flow because the balancing valve's too small, because it was never properly balanced to begin with. Alright, this is one that has a pressure readout, so you can see the pressure drop on it. This is one where it's circuit setter, where you set it, and then you have pressure readout valve. So this is a what do they call this? I'm going to draw a blank now. It's a special type of connection, okay, where you can take this port off, stick a needle in it, and it's a rubber gasket on the inside, so you can read the pressure, and then when you pull it out, it automatically seals. So it's a good way to, it's a very common pressure and temperature port, and I can't remember the name of it right now. But that's usually the type of port you'll have on a balancing valve. Flow meters actually meter the water flow through it, so you can have automatic flow meters, and they'll have different designs. This one is a Venturi tube, so the water goes through. It's got a throat on it, and it's kind of like a self-balancing valve. You'll see those sometimes. Butterfly valves are really only good. I mean, they make pretty decent balancing valves, not great, but butterfly valves make decent balancing valves. but they're really good as a pretty cheap shutoff valve. It's a very economical way to have a large valve instead of a ball valve. So you're going to have on a butterfly valve, as you can see, it takes up part of the port on a butterfly valve too, so they also need to be sized properly, but not as badly as some other designs. Whereas a ball valve, a full-size ball valve, will have full water flow through. A butterfly is going to restrict the flow a little bit, but it's usually not enough that it affects the piping system. So butterfly valves can be operating using a hand wheel with a gear drive, or they can be motorized. When automation is not required, a simple hand lever can be used. The mounting style, no holes for flange bolt, is called a wafer valve. So this is a wafer valve that just gets sandwiched in between two flanges, right? So that's a wafer valve, whereas the one with the flange holes, that's a butterfly valve. A wafer lug valve has openings for bolts passing through the two required flanges. Two flange styles are less common in HVAC applications, and then the others, two mating flanges raised or full face, depending on the valve style, are still required. And that's the other thing with butterfly valves, especially if it's not like a two flange type like this. You have to be very careful about the flanges you put on it, because if they're not lined up right, sometimes you can actually restrict the operation of the butterfly valve. Believe it or not, it's hard to do, but it's not that hard to do. Okay, so you gotta make sure that the valve opens and closes well. Alright, air separators. So this is a I'm gonna draw a blank again. This is a particular type of air separator. This is a very common one in commercial. It's a particular type. As the water flows through, slows down relative to its speed through the pipe, the air bubbles have time to rise out and collect at the top, right? So the water comes in, spirals down and out, and the air kind of ends up in the center and gets ejected at the top through the air separator. And I always forget which way's in and out on these things. I want to say it goes in the top and comes out the bottom. Yeah. I'm almost positive it's supposed to go in the top, come out the bottom. Read your instructions on them if you're not sure. But this is a very common type of air separator. Alright, an air control compression tank provides a cushion for the expansion of water. The air remains inside. So you have compression tanks and expansion tanks. Alright, a compression tank does not keep the air and the water separated by a diaphragm. The water, this needs to be the highest point in the system, if at all possible, or at least the highest point in the boiler room where this compression tank is located. And the water should be filled up about halfway in the tank, and the rest of it is going to be a cushion of air, and that provides somewhere for the water to expand. The water can push on the air, compress the air, and that allows for expansion. Whereas an actual expansion tank is going to have a rubber diaphragm, and it's going to be charged to a certain pressure on one side with air, and the water is going to be on the other side, and the water pushes on the diaphragm into the air. So remember, if the air and water are mixed in the same tank, it is a compression tank. If there's a bladder that separates it, we generally call that an expansion tank. Those terms are used interchangeably. A lot of times people will call a compression tank an expansion tank, but I always try and keep them separate in my head because how they're used is a little bit different, and the rules for installing them are a little bit different. So I think of compression tanks versus expansion tanks. I think that's a good thing to keep separate in your head. Alright, in air elimination, the air is vented directly out of the system. So if you have an expansion tank often, you will have, instead of going up to the compression tank, you will go up to an air vent, and this will just vent the air straight out. And these high capacity air vents have usually at least a 1/2 inch connection on them. Pipe these over to a drain, okay? Save everybody some headache, and pipe these things over to a drain for Christ's sake, so that you don't end up with water when it starts to fail all over all the damn insulation and stuff in there. It's very nice to pipe these things out over to a drain. Alright, they just vent the air out to the atmosphere. And like I said, oftentimes if you're set up like this, you will have an expansion tank instead of a compression tank. often, not always. All right, four pipe system. A four pipe system usually indicates that you can have simultaneous heating and cooling. You'll have water coils, and you'll have chill water coils and hot water coils. The chiller will go to one water coil. The boiler will go to another water coil in the same unit. You have double coil terminal units or air handling units, and they can provide heating or cooling at the same time. And depending on how they're set up, you can also do reheat for humidity control in them. So that is a four pipe system. Primary secondary systems, or a two pipe system. Oh no, wait, primary. Oh no. Sorry. Not talking right. So two pipe system will have one coil, and either the boiler or the chiller will be on at one time. I can't believe they don't say two pipe first, right? Alright, so yeah, you'll have a two pipe system, which only heating or cooling can be on at any given time. So they'll switch over between heating and cooling at a particular time of the year. Four pipe systems can do heating or cooling all year round. And then this is primary secondary loops. This is usually chillers or high efficiency boilers. So you'll have one loop that goes through the chillers or the boilers, and then you'll come off on a secondary loop to your terminal units. Alright, and then that's how you get the water from A to B. So it's always circulating here, and then these kick on as necessary, basically. Alright, any questions on any of that? Alright, last slideshow. When you complete this session, you should be able to do the following. Describe various commercial hot water heating system components and subsystems. Describe how a typical hydronic system is balanced. Explain basic concept of chill water systems and related components. Oh crap. Hold on. Need to share the screen, right? Make sure it's on in OBS. It is. Let me share the screen with you guys. Alright. Identify major components of commercial hot water heating systems. Before water system balancing procedure starts, the following preliminary steps should be taken. Obtain all the technical data for the equipment you're working on. You should always have that anyway. Study diagrams for the temperature control and piping circuits, and record the ratings and settings for various system valves. Review the operating and maintenance instructions for the equipment. Prepare a schematic layout of each system. Study the water system piping arrangement. Obtain all necessary instruments and calibration data. Complete a visual inspection of the system. There are numerous steps involved in performing a water balancing procedure. These steps can be summarized as follows: making sure all the preliminary checks and maintenance have been completed, ensuring all wiring, valves, gauges, and other equipment are functioning properly and set properly, recording system variables such as pressures, flow rates, voltages, and pump speeds, comparing those readings with the design specifications. The design specifications are very important because it takes not that much work, but it takes a reasonable amount of work to determine how much heat is going to be put out by each component in the system, whether it be fan coils or radiators or chill beams or whatever you're working on. The water temperatures and flow rates are what dictate the BTUs you put out. So you need to make sure that you're putting out the proper temperatures in the boiler system. And if you're doing outdoor air reset, you got to make sure the boiler system temperatures are proper for each outdoor temperature and the curves are set right. And you got to make sure you're providing enough flow through each of the individual system components in the system. So yeah. it's important to make sure that your balancing matches up with the original engineered design, whether you did it or an engineer did it. Alright, there are numerous steps involved in performing making preliminary adjustments to balance the system, rechecking variables, and repeating adjustments as needed. And that's one thing that a lot of guys skimp out on. After you balance a whole system, you need to go back and double check that it's all balanced, because what you do one place will affect another place. So usually it takes at least 2 passes on everything to balance the system out, because as you change the flow rate here, the pressure will increase, or the pressure drop will change, and the flow rate will change somewhere else. So anytime you're balancing something, you need to go through, rough balance everything, go back, fine balance everything, and then ideally go back and double check that everything's still good. Alright. Marking all components with final balance readings for future reference, checking safety controls, and submitting all necessary paperwork. Alright, chill water pump is located outside the chiller. Alright, so chillers, generally, you're going to have refrigerant, right? You're going to have refrigerant inside the chiller. And then your secondary refrigerant is water. Remember that term, secondary refrigerant. It's a very popular term used in chiller systems. Our primary refrigerant is whatever's in the chiller. And then our secondary refrigerant is our water, which carries the heat between the chiller and the rest of the system. Alright. So this is an air-cooled condenser. So this would be an outside condenser on a chiller, so there would be 2 pipes that go between the air-cooled condenser and the inside evaporative cooler on the chiller. So you have your whole refrigeration cycle here, normal refrigeration cycle, nothing real special about it, generally speaking. And then your water goes through the cooler, the evaporator, gives off heat, drops in temperature, and is circulated throughout the system to your air handler, where it picks up heat and goes back to the cooler. So this is if you have an air-cooled condenser. So really you'd only have a chill water pump. If it's a water-cooled condenser, we're going to have 2 water pumps, a chill water pump and a condenser or cooling tower water pump. The pump is typically located in a mechanical room, possibly with the air handling equipment. So here we're showing a air handler with the chill water pump. It's pumping through the unit, reciprocating liquid chiller unit on a roof, and we're just circulating between those. Alright, 2 basic classes of chillers. Mechanical, the most common type, uses some type of compressor, reciprocating or scroll compressors, centrifugal chillers or screw chillers. Or non-mechanical, does not have a compressor, uses a chemical cycle instead. That is your absorption chillers. I learned a lot about absorption chillers. Unless you're doing really big commercial, don't worry too much about absorption chillers. I wouldn't get too deep in learning about absorption chillers, because your odds of seeing it in the wild are pretty small. Alright, doesn't mean you might never, but I've never even ran across an absorption chiller. They're good in industrial applications where you've got waste heat you can utilize. Alright, air-cooled reciprocating and scroll chillers dominate the small to medium-sized chiller market. Centrifugal chillers are better suited for larger loads. They are traditionally water-cooled. So, in my experience, okay, just my experience, I typically don't see these large air-cooled chillers. You usually end up seeing a centrifugal chiller. I don't know if that's changing, but you know, most of your schools and stuff like that have these big centrifugal chillers in them with cooling towers and all that nice neat stuff. Alright, most screw chillers are direct expansion evaporators. DX evaporators, the majority are also air cooled. Alright, absorption chillers. In the absorption cycle, evaporation and condensation of the refrigerant water occur at different pressures. The absorption cycle uses a heat-operated generator to produce the pressure difference. Lithium bromide is a salt solution. The absorption cycle is based on 2 principles. Water can be made to boil in the 40 to 45 degree Fahrenheit range by maintaining a low absolute pressure of about 0.25 to 0.3 inches of mercury. Remember, the lower the pressure, the lower the temperature water is going to be boiled at. So you keep the water pressure at these low temperatures, and the lithium bromide absorbs the water vapor and exchanges the heat. Alright, again, I don't want to go into this deeply. Remember that lithium bromide is used in absorption chillers, and that's probably one of the most common questions you'll see asked about absorption chillers in general. Everybody likes to ask you the salt solution used in absorption chillers on these tests and stuff like that. It's always lithium bromide. Everything else, like I said, I've never seen one in the wild. Maybe if I actually ran across an absorption chiller and had to mess with one, I'd be more interested in them. But I feel like it's one of those things they make you learn for no good reason, because you just don't run across them very often. Alright, cooling towers, cooling circulating water. This type of cooling tower is very popular for commercial applications. It can be fitted with its own water sump or be positioned over a sump constructed above or below ground level. So this is basically just your run-of-the-mill cooling tower, your open system cooling tower basically. Your warm water is piped from your condenser, so you have your warm water goes from the pump and the condenser. You run the water through the condenser, run it up to the top of the cooling tower, let all the water drop down these plates basically through the decking, whatever you want to call it, and the air runs across it. So you make this water go into a spray so that it can exchange heat with the air, and that's basically so you can bring the water temperature down to whatever your wet bulb temperature is. So even though it's 72 degrees outside, right, 75 degrees outside, you can get this water theoretically down as low as 63 degrees, right, because you can get it down to the wet bulb temperature of the air. So you create a fine mist, as fine of a mist as possible, and you run the air across the water and exchange the heat between the air and the water. All this goes down, gets collected at the sump, and this cool water gets pumped back to the condenser and then pumped back to the cooling tower, and it just repeats that cycle, and the water cools the condenser. And it's a very efficient way of exchanging heat on a condenser, so that condenser, the cooler the temperature, right, the cooler the temperature, the more efficient the system's going to run, and you can get this water to a lower temperature than the actual air temperature, right, because of the heat of evaporation, the latent heat of evaporation, right, or latent heat of vaporization, if you want to say it that way. And that allows you to basically exchange more heat through latent heat removal, essentially. The point is that you can get it theoretically as low as the wet bulb temperature. So this is always going to be more efficient than an air-cooled system, which is why you see them on big systems. The reason you see these on big systems is because the bigger the system, the more it costs to run. The more it costs to run, the more every bit of efficiency saves you in money. So you want to make big systems as efficient as possible. The reason large chiller systems are used in commercial buildings is because it's a pretty efficient system. Alright, indirect contact water. So this is your closed circuit cooling towers. This is not going to be, as far as I understand it, and I'm not a cooling tower expert by any means. Baltimore Air Coil has some excellent guides on cooling towers, but my understanding is these closed circuit cooling towers are easier to maintain, but they're not going to be as good as your open circuits. But indirect contact cooling towers are also known as closed circuit towers. The water in the tower sump is separated from the water circulating in the condenser indoors. Evaporative condensers require more refrigerant piping and expose the system to far more refrigerant leak potential. However, they are popular for large ammonia-based systems. This would be an evaporative condenser. Is that it? Yeah. Alright, wrap up trade terms. An energy conservation arrangement used in chillers that accomplishes an intercooling of the refrigerant between the condenser and evaporator using a flash chamber or similar device. Flash gas of coolant produced in the flash chamber flows directly to the second stage of the chiller compressor, bypassing the evaporator in the first compressor stage. It is a flash economizer. We didn't even talk about that. I have no idea what that is. There you got it. There you go. That's something to read in your book, because I ain't nothing I can tell you about those. That's the first time I've ever heard that. Alright, lithium bromide. Again, just remember it because it's a salt solution commonly used in absorption chillers, and they love to ask questions on it on every HVAC exam you'll ever take. Only thing you need to remember about absorption chillers is lithium bromide, and everything else is useless information unless you're going to work on one. And if you work on one, give me a call, tell me what it was like, because I've never seen one in the wild. I think it's only going to be large industrial applications. Alright, any liquid such as water that is cooled by a system refrigerant and then used to absorb heat from the conditioned space without a change in state is known as an indirect coolant, or secondary refrigerant, or they say secondary coolant. That's a new one. Alright, secondary coolant, secondary refrigerant, indirect coolant. Those are the things people like to use water, like to call water in a chiller system. Alright, a thermal economizer is an energy conservation process used in chillers in which warm condensed refrigerant is brought into contact with the coldest inlet water tubes in a condenser or heat exchanger. This causes the condensed refrigerant to subcool to a temperature below the condensing temperature. Any questions on any of that? Alright, let's talk about what's going to be in your test on this one a little bit. Alright. A column of water. Alright, a column of water, how much does it weigh? Not how much pressure does it exert in PSI, but how much does it weigh? Remember the numbers we went through on that. We talked about if it was 1 foot high. We talked about if it was 2 foot high. You should be able to extrapolate that out and tell me how much it weighs, no matter how high it is. So remember that. Make sure you multiply properly. Do the equation. You should be able to do that. We're not going to do any practice on it. Hopefully you guys can remember that. Look at it in your book. Remember how to calculate the pressure of water and the weight of water based on how they told you in your book. And then I would practice other ways to do it and make sure you know how to do it yourself. You should always be able to look at a cylinder or a pipe full of water and tell me how much water is in it and how much that water weighs. Usually what I do is I do pi r squared to find the area of the cylinder. So you know if it's a 1 foot round pipe, right? And we started easy, it would be a half a square foot times a half a square foot times pi, which is 3.14, and that'll give me how many square feet is in the pipe, then how long it is, and that gives me how many square foot of water or cubic foot of water I have, and then you can look up how to convert cubic foot to gallons and then gallons to pounds. That's how I generally do it because I like to know how much water is in there in gallons for other reasons like introducing glycol and things like that. But you should have a good way to learn that, and we can talk about that a little bit more in another class if you guys want, if you remind me how to calculate volume in cylinders and pipes and things like that, but you should be able to do it. But for now, just remember how they told you to do it in your book because that's important. Alright, what is the static pressure going to be at the highest and lowest point in a building? And where is it its highest? Is it its highest at the top of the building? Is the pressure the highest at the bottom? We talked about that. Fluid rises. Make sure you remember that. Warm fluids rise. Alright, warm fluids rise. Feet of water. What is it a measure of? Right? What is it a measure of? When we say feet of water, what are we measuring? Remember I told you when we talk about feet of head, feet of water, what is that? An electrode boiler. Look up an electrode boiler in your book. We didn't talk about electrode boilers. Look it up and see what it relies on to heat water. Find out what a Scotch marine boiler is. Read that in your book. We didn't go over that, and I'm not gonna talk about it because I don't know anything about electrode boilers or Scotch marine boilers. So there's your homework. Read about those. Oh, there's a few things in here. What is this? There's a few things in here that aren't we didn't go over. All right. There are wearing rings on a centrifugal pump. Okay. I'm not an expert again in centrifugal pumps either. I'm a little bit more knowledgeable about the actual pumps, centrifugal pump compressors and stuff. I know even less about. I know a reasonable amount about pumps, but I've only rebuilt them a handful of times. But wearing rings on a centrifugal pump allow some fluid leakage. I'm sure there's a reason for that, but maybe look in your book. Maybe that's something I'll read about later. Wearing rings on a centrifugal pump allows some fluid leakage. What is this? Seems like an easy one, man. Oh, yeah. Remember I was telling you that when you're talking about a butterfly valve, you need to make sure that it can open and close when you install it. Generally, you'll want to install it with the butterfly open, and that is to try and make sure that you've got enough clearance that the valve will open and close, because sometimes if you install it closed, you'll find out it won't open real well. Alright, so the best thing to do with a butterfly valve is to install it already in the open position, or if you forget to do that, then make sure it opens and closes after you put it in, because you can have the alignment out enough that it won't open and close, and that's a bad day. Especially if you got everything else all set up and ready to go, and now you realized you left the valve closed the whole time and you can't get it open all the way. In a 4-pipe system, what type of valve is used on each double coil terminal? What? I'm too tired for this stuff, guys. Alright, two-way valve. Oh yeah, I know what they're getting at. So anyway, generally, it's just a solenoid, or it's just a regular valve. It could be a 3-way valve. It depends, man. It really depends on the design. I don't like to generalize things like that. But if you have a 4-pipe system, usually you're just going to have a 2-way valve on the coils. But you could have a 3-way so you can bypass to recirc. It depends. But they say 2-way valve, so I guess remember that. 4-pipe water system, usually the double coils have 2-way valves. Alright, when doing a water system balance, how should the final water flow rate at all units be set? Final flow rate. This one's a little harder than I thought. I saw some of the easy questions. I'm like, oh, they're easy ones. Alright, oh, I know what they're getting at. Alright, quick side note. Anytime you're balancing anything, okay, whether you're balancing water, you're balancing air, whatever the case may be, you're always going to be balancing to within 10 plus or minus 10%. It is hard, if it calls for 5 GPM, it is hard to get exactly 5 GPM all the time. You know what I mean? You're never going to get everything perfect on the whole system. You'll spend forever trying to balance a whole system perfectly. Usually, if you're within plus or minus 10%, anytime you're balancing anything, you're generally fine. Some counties do require you to balance within plus or minus 5% on airside systems and things like that. It's a little ridiculous, but it is what it is. So make sure you understand your local requirements, what they want from a balancing report, or what the engineer wants from your balancing report. But in general, most people, engineers, jurisdictions are fine as long as everything is plus or minus 10%. There's a couple reasons chillers are usually used in big buildings. All right. Those couple of reasons are efficiency, and it's less expensive to install all that piping than it is to install all the big ductwork you need. Okay. It is a more economical system overall. So that's why you see chillers. Remember the flash economizer we talked about? Flash economizers are often used on screw compressor chillers. The normal, alright, this is something we didn't go over either. The normal temperature, the normal water temperature on a chill water system that's used for comfort cooling, okay? The normal temperature of the water, you make sure I'm going to say what they say, yeah. The normal temperature of that water is 55 degrees. Alright, that's the return water temperature. The outlet water temperature could be 35, 45. It depends on the delta the system was designed for, what everything's designed for. But generally, the returning water is going to be about 55 degrees. Same, because you're generally shooting for 55 degree air, right? We're generally shooting for 55 degree air. So if we've picked up all the heat we could out of that chill water system, we will be at 55 degrees coming back. So 55 degrees in general is our commercial magic number, right? 55 degree air coming out of our supply, 55 degree water coming back to our chiller, all that nice neat stuff. Alright, centrifugal liquid chillers. Alright, so centrifugal chillers, usually lower pressure refrigerants and things like that are your centrifugal chillers. They're very, very common. Alright, there's a lot of things that, there's a lot of important things about them that you should learn. They're basically just like any other refrigerant cycle, but there are some quirks to them. There's a lot of quirks to them that we haven't talked about. So if you do a lot of chiller work, you want to read up a lot on centrifugal chillers to make sure you understand things like purge units and, inlet slide valves, which are going to be, inlet guide vanes, which are going to redirect the refrigerant to control capacity and things like that. There's little quirks about them that you need to know, but always remember it's still just a refrigerant cycle. Okay, it's nothing to get overwhelmed from when you got to walk up to a chiller, but try and make sure you understand the special components that are generally on them, especially the centrifugal chillers, because those are the ones that are a little bit more daunting if you've never worked on them. All right. And then the last thing is evaporative condensers. Evaporative condensers are generally going to be used for refrigerated food. So make sure you remember that. All right. If you got an evaporative condenser, it's usually used for lower temperature refrigeration applications like refrigerated food. All right, that's about all the steam I got, guys. I'm beat. Any questions?